The Internet Protocol, IP, has a helper protocol known as ICMP, the Internet Control Message Protocol. As the name indicates, ICMP is used to send control messages, whether they are error messages or messages to do something, a command of sorts. ICMP is viewed by many as more than a helper protocol. It's viewed as a twin protocol, because if you implement IP, you also have to implement ICMP. In this video, we will look at ICMP to see how it works, but we will also use it to highlight some issues of IP that we haven't had a chance to talk about yet. So in terms of studying, in terms of remembering things that you need to look at, you can use ICMP as a framework to remind yourself of these additional things. ICMP is defined in RFC 792. It's been updated since that very old standard, and we will look at the RFC in a moment or two. But to give you a feeling of how ICMP works, let's think about it in the usual terms. ICMP, like almost every other protocol that we've spoken about, consists of a header and a payload. And in the header, we in essence put two values. Sometimes it may be a bit more, but there is a type. There are only so many control messages that you can send out that they decided to number them. And there will be a message number 0 and a message number 1 and so on. So no further details have to be provided. You're simply going to say, I want you to do whatever IP message 8 or ICMP message 8 means. And in some cases, there will also be a code, which is just another number that modifies the behavior or that provides you with more information about the specific type. So the code will depend on the type, and the type is a simple number. Those go into the header, into those two positions. There's also a checksum over the header. And that's basically it. It is really a simple protocol. One question to think about just for a moment is, how are we going to get this message to the other side? And the answer is that it will use IP to get it to the other side. So it almost seems as if it is on a higher layer than layer 3, as if we have to put it on layer 4. But this isn't a transport protocol at all. This is intended to help IP. So even though these packets become the payload of an IP datagram, they are also deemed to be on layer 3, just like IP datagrams. Here we are looking at the RFC for ICMP, that is RFC 792. This is the almost original, dating from September 1981, and it was written by John Postel. His name is hidden behind my picture in the top right-hand corner. What you can see in the RFC is firstly the name of the protocol, but then a little bit later on, when you read the initial couple of lines, you will realize that they are talking about gateways, not routers. We nowadays would probably talk about routers rather than gateways. You've already seen the notion of a gateway when we spoke about a default gateway. Occasionally a gateway, or a router then if you prefer, a gateway or a destination host will communicate it with a source host, for example, to report an error in datagram processing. For such purposes, this protocol, the Internet Control Message Protocol, or ICMP, is used. You can also see the claim that ICMP uses the basic IP infrastructure, but it is not a higher layer protocol. It really forms part of the IP setup. There are also in the following paragraph a couple of examples provided of when an ICP datagram will be sent, what the reasons are. Perhaps more important for our purpose right now is ICMP will often report errors, but its intention is not to make IP reliable. IP is an unreliable protocol in the sense that we described unreliable on layer 4. And in this case, when ICMP does report an error, it's not something that is done in order to make it reliable. Also, in many cases, reporting an error will be optional. It's not something that has to be done. Let's look at the various ICMP messages that can be sent. And almost at the bottom of the RFC, it's just above the references, you will see the list of ICMP messages, in particular ICMP message types. And that is echo reply, destination, unreachable, and so on. We've copied those to the panel on the right-hand side of the screen so that we can keep track of them as we progress through our discussion of ICMP. The first options or the first types that we will look at are the pair echo and echo reply. Echo is message number 8 or type 8, and echo reply is type 0. What you can see when you look at the RFC is that the header indeed consists of a type. So the type would be 0 for echo reply and 8 for echo. Often I will talk about 8 as echo request, because you send out the echo request and that is followed by the reply. But the correct name for echo request is just echo, as you can see it on the screen right there. So the type will be an 8 or a 0. The code is not used in this case. There is a checksum that fulfills the normal function. And then there will be an identifier and a sequence number. So the idea with this is that if you send out multiple echo requests, you can receive responses and you can see which request is associated with which response. So that's where the identifiers and the sequence numbers come into play. Scrolling down a little bit, you can indeed see that type 8 is for the echo message and 0 is for the reply, and the code is always 0. No other options are provided. Now, the easiest way to see this in action is the ping command, and every modern operating system provides a ping command. So if I, for example, want to ping one of my own computers, then I would simply say ping 10.1.1, happens to be on my own local subnet. I should get some responses back. You can see the default behavior for ping in Windows, in the command line interface of Windows, is to send out 4 requests, and we've received 4 replies. You can see the times that they took to respond, 1211 milliseconds, and you can also see a TTL field there, time to live, which is 64 in this case. We will talk about time to live later on. In fact, if we ping a machine out there, let's say we ping the Google DNS server, a public DNS server, then we would expect this to send out 4 requests. And what you can see here is that the time to live is now only 58. It's no longer 64. Again, we will explain that a little bit later. you can see that the response time, the time it took for the echo request to go out to Google and to come back, is now significantly longer. We're talking about 7 milliseconds and 5 milliseconds, whereas it took only about 1 millisecond on my internal machine. The way in which this works is pretty much the same in all operating systems. If we use a different machine, in this case a Linux machine, I can again ping 10.1.1.1, and we will get some, that's very, very fast response times. I happen to be on 10.1.1, that's why I'm getting those extremely fast response times. And you can see the behavior in Unix or Linux is just to continue pinging, and I have to break it to stop the pinging. I have an option in Unix to say how many ping messages I want to send out, but the default behavior is to just continue pinging. In Windows, the default behavior is to send out 4, but I can also specify an option that will force it to continue pinging until I stop it, until I interrupt it. Linux is just 2 response times, and you can, we'll talk about time to learn that they took to respond to pinging. To stop, and I have to break. The ping command is an extremely useful debugging tool. One of your challenges when the network is down is to figure out what the problem is. And with layer 3 more or less in the middle of the protocol stack, ping enables you to ping another site, and if you get a response back, you know the lower layers of the protocol stack work. If you don't get a response, the problem is in the lower layers. If you do get a response, your problem is in the higher layers, and that halves your search space for your problem. The next example to look at is destination unreachable. That is ICMP message type 3. Looking at the header, you will see that this again consists of a type, a code, a checksum, just like the previous case. There's an unused block, and then there is the header of the message that causes the problem. So as you would expect from destination unreachable, that is a message that you would send out, or that you would expect to receive if you've sent out a message and it cannot be delivered because its destination is not available or is not connected. So as a response, you are getting this error message, and you are getting the initial part of the message that cannot be delivered. If you look at the code field, so it's type 3 that identifies this as destination unreachable, but the code tells you what is wrong. So net unreachable would be code 0, host unreachable would be code 1, protocol unreachable code 2, and so on. 2 things to point out there. Number 4, fragmentation needed, and the do not fragment flag is set. So the packet is too big, but there's a flag that says you cannot fragment it. We will talk about fragmentation later on. And then number 5, the source route failed. Remember when we spoke about bang addressing in an earlier video? We said that that is source routing. That's where the source, the sender of the message, specifies the route that it should follow. So here is clearly provision that is made for a source route that was specified but which is not used. We'll touch on source routing again within a moment or two. To make this again practical, if I, for example, ping a machine 10.1.1.4, it's one of the machines on my local network, this happens to be a machine that is turned off at the moment, so it should not be able to respond. And pinging it, what we are getting back is a message that tells me that the destination host is unreachable. So my network is operational, There's no problem with the network as such, but it can't get to that host. Looking back at the RFC, you can see that code 1 is the one that indicates that the host is unreachable. So that's the error message, the ICMP error message that we received, and that was printed out below my ping command. We will not discuss all of these ICMP messages. We'll leave it up to you to look at them. On the screen at the moment, you can see the source quench message. That is a message that a recipient can send out if packets arrive too quickly. So it basically tells the source of that message, the sender of that message or of those messages in the end, to slow down, to wait a little bit longer between packets that are sent. It may be because a router is too busy, that the router will send the source quench to the source node, or it may be the destination that doesn't have the ability to process more IP packets right now, or at least not at the rate at which they're coming in, and it tells the destination or the source to slow down a bit. The next one on our list, not going to scroll to it, but it is redirect. And that is a mechanism where a router can tell a sender or another router that there is a shorter path to a destination than going via it. So it informs the sender of better options. You can go and look at the details in the RFC. Let's look at time exceeded in a bit more detail. So there is the time exceeded message. This is, as the name suggests, an error message that would be sent if some time expired. Clearly, it's type 11, so message 11 indicates time exceeded. If you look at the header, you can again see that there's a type of code checksum, as we've seen in all the cases. There's again an unused portion, and then there is the header of the datagram that caused the problem, the one that somehow exceeded its time. To figure out what we mean by time exceeded, you will see that there are two options that are indicated by two codes. 0 talks about the time to live that has been exceeded, and 1 indicates a fragmentary assembly that took too long. We're not going to talk too much about the fragmentary assembly. In fact, you can go and read up on what it is. But the time to live exceeded is rather important, and let's look at what that means in a bit more detail. Let's talk about this notion of time to live. What may go wrong in IP is a scenario like the following. Suppose we have some router, and let's call that router A, and we have another router, and let's call that router B. And then there's some computer, and that computer may be Z or whatever. I'm not really too concerned about it right now. The routing table at router A, may indicate that if you want to go to Z, the best hop or the best route is to go to B and take it from there. The routing table at node B or at router B may indicate that if you want to go to Z, then the best option you have is to go to A. Now, clearly this is going to cause problems. This may be static routing that has been set up incorrectly, or it may be a typical router like a RIP router that just happens to be out of sync right now because it's not properly updated its values recently. So what will happen here is if a packet arrives that says, I want to go to node Z. So this packet arrives at node A. Node A will consult its routing table, and it will say, okay, I have to send it to B. And node B will consult its routing table and say, okay, I have to send it to A. And A will consult its routing table and say, I have to send it to B. And B will consult its routing table and say, I have to send, and then you can just see the mess as these routers are playing ping pong with this message. and it's on that piece of wire or whatever connects A and B the whole time. Now, to make matters worse, in the meantime, other messages also intended for Z will arrive, and B will also send them to A, and A will also send them to B, and over the next 5 minutes or over the next year, millions of messages may arrive, and they may all sit on this network, jumping to and fro between those two nodes without ever going anywhere. And they're just clogging up the network. There's no way that the network can repair this unless the routing tables are updated. So all the traffic for Z will get stuck between those two nodes, between those two routers, if it ever gets to any one of them. The solution to that problem consists of two portions. The one portion is that the IP datagram includes a time to live field in its header. And that time to live field is initially assigned some value. A popular value may be something like 64. And then every time that a router forwards that packet, that becomes, or it decreases the time to live by 1. So if this packet comes in from out there and its time to live is 64, it will be forwarded to B with a time to live that is now 63. And then it will be forwarded to A with a time to live that is now 62, and so on. So every time it is forwarded, it is decremented by 1. The moment when it becomes 0, the packet is discarded. It's just thrown away. So what it means, the packet will only be sent, if its time to live is initialized to 64, it will be sent up to 32 times in that direction, up to 32 times in that direction, and then it will be discarded. So what we are solving here is this build-up of traffic that is not going anywhere. It is simply deleted or discarded the moment when it becomes 0, when the time to live becomes 0. Time to live is used to solve a problem that would otherwise cause other problems in the network. It discards packets when they've been on the network for too long. But there is a rather innovative way of using time to live to determine the route between you and some destination. Suppose you send out a packet, let's say it's an echo request, and you start it with a time to live of 0. The time the moment it gets to the very first router on your network, it will have expired, and if you're lucky, then the router will send back a message to say, this packet has been thrown away because it expired on the network, and therefore you know what the very first router is. And then you send out the same packet again, but this time with 1 and a 2 and a 3 and a 4. And hopefully all the routers, every time it will get one hop further before its time expires, and it will hopefully report a message. Now, that functionality has been built into a tool with the name Traceroute. We're looking at Windows command line interface right now, and in Windows the command is simply traceRT. What I'm going to do here is to specify an option to say, do not resolve these hosts for me. In other words, only print out their IP addresses, don't print their names. And the only reason why I'm doing that is because I don't want the screen clobbered with information about names. At the current font size I'm using, it's going to give me a lot of information that's just going to make this hard to read. I'm also going to ask it to go to f.rootservers.net. That is one of the root servers in the DNS, as you should recall. And I am effectively asking my computer now to send out echo request packets and increment the time to live until we get to frootservers.net. So there we see our first response. It's from my internal router on my home network. Then on response line 2, we see that we're not getting any response back. Clearly it's discarded, but it's not reporting it to us. And then as we move along, you can see that the other routers that are available that are on this path responding until frootservers.net responds to me, and I've got this entire path. Interesting here to note that frootservers.net is 7 hops away from me, so an initial value for time to live of about 64 should be enough. In fact, if machines are 7 or 8 or 9 hops away from me, I may start with a value of 32 and use this as a little bit of a challenge for yourself to see what is the longest path you can get to some router on the internet. To look at this from a slightly different perspective, let's use one of my Linux computers and specify that I want to trace the route. On Linux, you may also want to look at trace path as an alternative, but I'm going to use Traceroute here. In this case, there isn't an easy way to suppress the resolution of names, so I'm going to get the names printed out, but and you will see how that will fill up the entire screen and make it harder to read, but it will also be informative in many ways. So again, tracing the path to frootservers.net, and you can see that we've received responses from it, this time with the names. So my router responded initially, and then a couple of other routers responded. There at step 5, a Cloudflare responded in the Joburg top-level domain. Something in the Joburg top-level domain would probably be in Johannesburg. So at point 5, it responded from Johannesburg, and at point 6, it was already at frootservers.net, which suggests that frootservers.net is directly connected to that machine in Johannesburg. I wish we had time to talk about Cloudflare. It is something that I recommend you learn more about, but we probably won't have the chance to discuss the notion of Cloudflare. It is a tool that is used in to counter distributed denial of service attacks. I'm going to do a similar trace route to frootservers.net, and this time I'm going to trace the route from a computer that happens to be in the United States. So if I say Traceroute, and again I want to go to frootservers.net, and you can see how it responds. There seems to be a little bit of a delay. At step 5, the machine doesn't want to talk to us for some reason or another, so it's not sending out those error messages. But what you do see here is that I started out with the machine in the United States. At step 3, it was at LAX, that's Los Angeles, sounds like the airport code, who knows. At step 4, it was again at some Los Angeles site. 5, we don't know. 6 doesn't tell us where it is. And then it was at frootservers.net. It was 6 steps in Johannesburg to get, or from Pretoria to get to Johannesburg, to get to frootservers.net. Here to get from somewhere in the desert in the United States to frootservers.net took 7 hops. So it also seems to be located very close to that machine. One of the tricks that they are using for these very important machines nowadays is to give the same number, the same address to different machines that are synchronized. So frootservers.net is no longer a single machine that sits somewhere in the world. frootservers.net, with its associated IP address, is replicated right around the world. And the routing tables are set up so that you will be routed to the closest one. That is, in a sense, a contradiction of how IP addresses were intended to be used. Apart from the private addresses, the same address was not supposed to be reused for multiple purposes, but for high availability machines, in other words, machines where you need high availability. The internet is nowadays configured so that the same machine effectively can be replicated across different machines, placed at different locations, and you will then be routed to that very same IP address, but a very different machine situated somewhere else in the world. Another observation here is that from my local machine in Pretoria, it took me 6 hops, according to Linux, to get to frootservers.net. But from the Windows command line, it took me 7 hops. It's on the same network. Here we didn't get the response from machine 2. On the Linux side, we got a response from everybody when I traced it from my home. So there's clearly a difference between these two responses, and it would be a nice challenge for you to try and figure out why that happens, to see whether you also get this difference between Windows and Linux. We are not going to discuss the remainder of the ICMP messages. We have the parameter problem, message type 12. We have the timestamp request and reply, types 13 and 14. And we have the information request, response and reply, types 15 and 16. You can go and read the RFC and see what they're about. A little bit of a challenge, if you want a challenge, to go and look at the specification of information request and reply and see whether you can figure out what that means by reading the RFC. We promised to say one or two things about fragmentation. IP packets will eventually be passed down to layer 2, just like any other layer will pass packets down to the layer underneath it. And on layer 2, we will sometimes get size constraints. The biggest packet that you can send out is 1 kilobyte long, or whatever that size may be. An IP packet may be far too long for the lower layer to handle. And what IP will do when that is the case is it will fragment the packet. It will literally slice it up into packets that are small enough so that they can be carried by layer 2. When IP fragmentation occurs, it simply takes the packet and it slices it up. And the rule says that once this packet arrives at the destination, it should be reassembled. At this stage, we can begin to think about what an IP packet looks like. Again, my philosophy is that one should know more or less what to expect in an IP packet, and exactly where it is, at exactly which bit or byte position it is. If you need that, you can look that up in a manual. But in principle, what goes into the IP packet? So the IP packet or datagram, again, will have the usual layout that we've encountered all over the place. The payload will be the segment that came from layer 4 above, and what we are interested in here is what goes into the header. Clearly, since this deals with routing, remember that key concept, we will have a source address in the header, and we will also have a destination address in the header. We will have, as you've seen just now, have a TTL, time to live value in the header. We will have a couple of flags, and some of those flags will deal with fragmentation. And as you will see just now, one of them specifically is a flag that you can say that this packet should not be fragmented. And then a key element of all of this, in fact, this is the one field that you may remember the position of, and that is the version. The very first byte in an IP header is the version. And today we've been talking about version 4, as we have for a couple of videos now. And clearly, when we move on to IP version 6, it will share that very first field. But for it, the version will be 6. And then the rest of that IP packet will be entirely different. It will be whatever IP version 6 prescribes. We will look at IP version 6 in the next video. So here we have the complete IP version 4 header. As promised, you can see that the initial field is the version number. It's not a byte, as I've just said, it is a nibble. Then there are a couple of parameters that you can go and look at. We're not going to talk about every field in the header. The total length is something that should make sense, the length of this datagram. There is an identification field that you can look at. We mentioned the flags briefly, not much detail that we're providing here. And there's the fragment offset. So the fragment offset is if this packet has been fragmented, where does this one fit into the bigger whole, into this bigger entity? If it's 0, it means it's right at the beginning of the entire packet and so on. So how far from the beginning is it? Then there is a time to live that we spent some time on discussing. Next field that you see here is the protocol. Now the protocol refers to the protocol that it is carrying as the payload. In other words, TCP or UDP or some other protocol. That makes sense. The question that arises is rather, why didn't we have anything like that in any of the previous headers that we looked at? Then we see a header checksum. IP, as we noted, is unreliable. And just like UDP, which is also unreliable, but on layer 4, this only checks the header. It doesn't try and protect the contents of the datagram with a checksum. Then there is a source address, as we expected. There is a destination address, as we expected. And then there are a couple of options. And those options can modify the behavior. One of the interesting options that is provided by IP is source routing. And if you specify in that option field that you want to use source routing, you can predetermine the route that the IP packet will follow. It should ignore the routers along the way. However, hardly any router on the internet nowadays supports source routing, and therefore the option has become effectively useless. Because the options may include a number of variable length fields, such as the route that is to be followed, some padding may be required to get it back onto a word boundary, and that's what the padding does. This concludes the discussion of IP version 4. We've only scratched the surface. You should use tools like Wireshark to inspect IP packets, see what occur in the packets that you are actually seeing on your network, and so on. What remains for us to be done or to discuss in this series is IP version 6.
Music you.